Hi everyone, my name is J.Arora and I am a PhD student at Sister Labs Portugal. So here I present our work, Bus-Contention Aware Schedulability Analysis for the three-phase task model with partition scheduling. So this is the outline of the presentation. Firstly, we will discuss about the motivation for the proposed work. Then we will present the introduction. Further, we will define the specific problem in the context of this work. Then we will present the main contributions of the proposed work. Then we will present the bus blocking analysis and worst case response time analysis. Finally, we will discuss the experimental results followed by the conclusion and future work. The multi-core processors offer several advantages over single-core processors, such as raw computing power, energy efficiency, and it is possible to build cost-effective solutions using such processors. Many soft real-time applications have adopted multi-core processors to take advantages of these features. However, the use of multi-core processors in hard real-time systems is discouraged. The main reason is the multi-core systems has the shared system bus, shared cache, and the main memory that can bring the temporal unpredictability in the system. To understand this, assume that we have a dual core processor in which both the cores shared the system bus, shared cache, and main memory among them. So a task may suffer contention at the shared cache, at the system bus, and at the main memory while accessing these shared resources due to the ongoing execution of the co-running tasks. In this work, we particularly focus on the contention caused by the co-running task while accessing the shared system bus. This is important as the system bus is responsible to connect all the cores to the main memory. The three-phase task model was proposed to circumvent the problem of unpredictability caused by the shared resources in multi-core processors. In the three-phase task model, the execution of each task is divided into three phases. That is acquisition phase, also known as A phase. In the A phase, task access the system bus and fetch the data from the main memory and store it in core's local memory. In the execution phase, also known as E phase, the core executes the data as per the data available in the core's local memory. Finally, the restitution phase, also known as R phase, that executes to write back the modified data to the main memory. So A and R phases are the memory phases in which access to the shared system bus is required, whereas the E phase does not require access to the shared system bus. In multi-core systems, a core can execute a memory phase at the same time when tasks running on other cores are executing E phases without suffering any blocking at the system bus. So in this example, the task running on core 1 is executing its A phase by accessing the system bus when the system bus is free. Once the A phase is completed, the core 1 will release the bus and will start executing E phase. Similarly, at the same time, task 2 running on core 2 can execute a memory phase and then followed by the E phase. So by this, the unpredictability caused by the shared resources is circumvented up to some extent. Even though three-phase task model attempt to circumvent the unpredictability caused by the shared resources, there can be a scenario in which the three-phase task can suffer bus blocking. This situation happens when a task wants to execute a memory phase by accessing the system bus and the system bus is busy serving the memory phases of co-running tasks. So in this example, right now the bus is free, so task running on core 1 access the bus and start executing A phase. If at the same time instant a task running on core 2 wants to access the system bus to execute a memory phase, it will suffer the bus blocking because the bus is busy serving the request of task running on core 1. Once the task running on core 1 release the bus, then only core 2, the task running on core 2 can execute the A phase. Similarly, once the task running on core 1 is executing R phase, and at the same time instant the task running on core 2 completes its E phase and wants to access the system bus to execute its R phase, it will suffer bus blocking, as the bus is busy serving the memory phase of task 1 running on core 1. So this bus blocking is dependent on number of memory phases that execute on the core under analysis, and on the other cores, the size of memory phases, task priorities, and bus arbitration policy. The possible consequences of this: it can bring temporal unpredictability in the system, and a task can possibly miss its deadline, that can eventually lead to a catastrophic failure in case of hard real-time systems. There are work that exists that focus on bus blocking problem in three-phase task model for global scheduling. However, no work exists that focus on this problem for partition scheduling. Therefore, we fill this gap by proposing the solution for bus blocking problem for the three-phase task model in partition scheduling. So as our first contribution, we propose a fine-grained analysis to compute the maximum bus blocking for the fixed priority three-phase task model executing under partition scheduling. Then we propose a schedulability analysis for three-phase task model by integrating the impact of bus blocking. Finally, we perform a set of experiments to understand the effectiveness of the proposed approach. In the state of the art, it has been proven that to compute the worst case response time of a task under fixed priority non-preemptive scheduling, it is necessary to compute the response time of each job of the task tau I that executes within the longest level I busy window. The level I busy window is the longest period in which the workload due to higher or equal priority task is positive and zero at the start and at the end of the interval. So for single core processors, the longest level I busy window can be computed by considering the maximum blocking that may suffer due to the lower priority task and maximum interference that may happen due to higher or equal priority task running on the same core. However, in case of multi-core, it is possible that the jobs that execute within the longest level I busy window may suffer bus blocking from the core running tasks. So in this case, the longest level I busy window not only depends on the task running on the same core, but also dependent on the task running on the other cores due to bus blocking phenomena. So now we will see that how to compute the bus blocking. So now we will discuss the proposed bus blocking analysis. We know that to compute the maximum bus blocking suffered by a set of jobs running on the core under analysis, we need to compute the maximum number of memory phases that may suffer bus blocking and the maximum number of memory phases released on the remote core that can cause bus blocking. Since the memory phase is a part of a job, we compute the maximum number of jobs of core under analysis that may suffer bus blocking. Similarly, we derive the maximum number of jobs released on the remote core that can cause bus blocking in a given time interval. Once the number of jobs released on the core under analysis and the remote core is bounded, the maximum bus blocking can be obtained for three possible cases. Case 1, in which the number of jobs of core under analysis is greater than the number of jobs released on the remote core. Case 2, in which the number of jobs of core under analysis is equal to the number of jobs released on remote core. Case 3, in which the number of jobs of core under analysis is less than the number of jobs released on the remote core. So in case 1, we argue that if the number of jobs of core under analysis is greater than the number of jobs released on the remote core, then all the memory phases released on the remote core can participate in the bus blocking. We explain this argument using an example scenario. Assume that there are 3 jobs that may execute on the core under analysis, and there are 2 jobs that are released on the remote core. So in such an example, it is possible that all the memory phases that are released on the remote core can participate to the bus blocking. So if you can see, the first blocking is composed of A phase of the first job, whereas the second bus blocking is composed of R phase of the first job and A phase of the second job, and finally the third bus blocking is composed of R phase of the second job. So in such a case, the maximum bus blocking can be derived by considering sum of all the memory phases that are released on the remote core in any time interval of a given length WIL. In case 2, when the number of jobs on the core under analysis is equal to the number of jobs released on the remote core, then we argue that all the memory phases released on the remote core can participate except one. So we explain why one of the memory phases cannot participate to the bus blocking. We explain this using 2 example scenarios that may happen in this case. So in possible scenario 1, assume that the core under analysis execute 3 jobs and 3 jobs are released on the remote core. So in such a case, if the A phase of the first job participates to the bus blocking, then the bus blocking is like first bus blocking will be composed of A phase of the first job, whereas the second bus blocking is composed of R phase of the first job and A phase of a second job that executes on a remote core. Finally, the third bus blocking is composed of R phase of the second job and A phase of the third job. So in such a case, A phase of the first job participates to the bus blocking, but R phase of the last job released on the remote core within this interval WIL cannot participate to the bus blocking. Now we present possible scenario 2 that may happen under this case. So 3 jobs are executing on core under analysis and 3 jobs are released on the remote core within the busy window. So if the first blocking is composed of R phase of the first job and the A phase of the second job, and then followed by R phase of the second job and A phase of the third job, and finally the R phase of the third job contribute to the bus blocking. So in this case, the R phase of the third job or R phase of the last job contributes to the bus blocking, but A phase of the first job do not participate to the bus blocking. So in this case, there can be two possible scenarios. Either the A phase of the first job do not participate to the bus blocking, or R phase of the last job of the remote core do not participate to the bus blocking. So we do not know that which specific job running on the remote core will execute at the first or in the last. So to compute the maximum bus blocking, we consider the sum of all the memory phases released on the remote core except the smallest memory phase. Finally, in case 3, if the number of jobs of core under analysis is less than the number of jobs released on remote core, in such a case, the remote core can cause at most number of bus blocking, which is equivalent to the number of job executed on the core under analysis. To understand that how to compute the maximum bus blocking in this case, we show an example. Assume that there are 5 jobs that execute on the core under analysis, and there are 8 jobs that are released on the remote core that can cause bus contention. Now in this case, we know that the maximum bus blocking is dependent on the maximum number of jobs that can suffer bus contention. So in this case, we will extract a specific jobs that has the memory phases with maximum execution time that can possibly cause the bus blocking. So we extract a set of memory phases with maximum execution time from the jobs released on the remote core. Once these memory phases are extracted, then we compute the maximum bus blocking by considering those extracted memory phases released on the remote core. So the maximum bus blocking in this case is derived by extracting the set of memory phases released on the remote core with maximum execution time that can cause bus blocking to the core under analysis. Now we will present the bus contention aware worst case response time analysis. To compute the worst case response time of a task tau I, firstly we have to build the longest level I busy window. Then we have to analyze the number of jobs that may execute within the busy window that belong to tau I. So in this example, assume that there are two jobs of tau I that execute within the longest level I busy window. So we have to analyze the response time of both the jobs to compute the worst case response time. So in order to compute the response time of a given job of tau I, let's assume we want to compute the response time of a second job of tau I. So firstly we have to consider the maximum blocking that can be caused by the lower priority task running on the same core, and maximum interference caused by the higher priority task running on the same core, and the previous jobs of tau I. Now in case of multi-core, it is possible that all the jobs that executes during the response time of second job of tau I may suffer bus blocking from the core running tasks. So in this case, we have to compute the maximum bus blocking suffered by all the jobs that execute during the response time of a given job of tau I and integrate its impact in the worst case response time. Now we will discuss the experimental evaluation. So we performed a set of experiments on the synthetic task set to understand the effectiveness of the proposed approach and compare it with a similar work from the state of the art. So these are the default parameters. The number of cores by default are 4. The set of tasks in the system is 32, in which each core has 8 tasks. Task utilization is assigned randomly using U-Unifast discard, and task periods are assigned randomly in the range of 100 to 1000 using log uniform distribution. So in the first experiment, we varied the task set utilization from 0.05 to 1 using the proposed approach and the state-of-the-art approach. We observed that up to 29% of task set were more schedulable using the proposed approach. This can be due to the fine-grained bus blocking analysis proposed in this work. The state-of-the-art provides a safe upper bound on the memory interference, but it does not consider different cases that may happen in practice using the number of jobs released on the remote core and the core under analysis. In experiment 2, we vary the number of cores along with the task set utilization. We varied the number of cores from 2 to 8. We observed that with the increase in number of cores, the overall schedulability is decreased using both the approaches. This can happen as the number of tasks running in the system increases with the increase in the number of cores that may eventually cause more bus blocking. Still, for all the values of M, the proposed approach performs better than the state-of-the-art approach. In experiment 3, we varied the memory demand of the task sets from 5% to 95% along with the task set utilization. We can see with the increase in memory demand, the overall schedulability is decreased using both the approaches. This is intuitive, as when the tasks in the system have more memory demand, they can cause more bus blocking. Still, for all the values of task set utilization and memory demand, the proposed approach outperforms the state-of-the-art approach. Similarly, in this experiment, we vary the task period ranges and observe the schedulability using the proposed approach and the state-of-the-art. And we can see for all the ranges, the proposed approach outperforms state-of-the-art. To conclude, In this work, we proposed a fine-grained bus blocking analysis using different cases and sub-cases that may happen in practice. Then we formulate the worst-case response time by integrating the impact of bus blocking. Experimental results reveal an increase of up to 34 percentage points of schedulable tasks in compared to the compared approach. For the future work, we would like to extend our work to support different bus arbitration policies and evaluate its performance using benchmarks and industrial case studies.